All right, my friends, last section of the school year for Calc BC. We're going to talk about Section 9.5 in a couple parts. Part 1 is an introduction to the area in polar coordinates. Just so you know, I've asked one of your classmates to come and help me today because writing with my left hand is just not going to happen. And so Bryce Layton is here. He's going to be literally my right-hand man. And anyway, so bless his math heart, he's here to help me out with this very last lesson. Thank you, Bryce.
Yeah, you're welcome.
Anyway, so your warm-up here is find the area of the sector of a circle with a radius of 5 centimeters that is formed by the interior of a central angle with a measure of 3 radians. Up to you whether you are going to pause the video and do this on your own or not, or just luxuriously watch someone else do it. Anyway, so in case all that vocabulary is just a bunch of math words, Bryce is going to go ahead and draw a picture of what it's saying. So you have a circle, radius 5 centimeters, and then your central angle just means its vertex is at the center of the circle, has a measure of 3 radians, and I hope it makes sense. He drew it so it's almost half the circle, since half would be 3.14 or so. Okay. And then we're finding the area of this piece here. There we go. All right. So to do this, you could set up a proportion, or there are lots of ways, but Bryce is going to demonstrate setting up a proportion where you do one fraction that shows the numerator is the angle measure that is used for the sector. You divide by the angle, change in angle that takes for 1 full rotation of the circle. So you have, this is a portion over the whole type fraction. Now we're going to do the same thing, but for, that represents area. So we're going to do A for area over, and then we're just doing pi r squared. In this case it would be 25 pi. So a quick look at this. You've got portion over the whole with angles, and then you have portion over the whole with area. Then just solve it using whatever method makes sense to you. So in this case, we'd find that the area is 75 over 2 square centimeters. There we go. Now let's take this concept and then do this in general, where what if instead of 3 you wanted to do this for any angle measure theta, and then what if instead of 5 you wanted to do this for any radius measure r? Then in general, the area of a sector in radians mode.
Oh, frick.
It's okay, just
No.
write in. It's good, just keep going.
All right, all right. All right.
Is, so instead of 3, you just put theta divided by 2 pi equals just the area you're finding, so A for that, divided by, and then pi r squared. There you go, solve for A, and you've got it. There we go. So here's a nice little formula. If you need the area of the sector of a circle, given with any radius and any angle measure, then you could just pop things into this little formula and have it done. I hope you know that this is not supposed to be a geometry lesson. This is supposed to be a calculus lesson. So let's talk about where we're going with this. So we're going to talk about if you have a polar plane, and you have any given polar graph on there. We're going to keep this nice and generic, so let's say that this is the graph of r equals some function of theta. And we're going to be finding the area bounded between a ray, which would have an equation theta equals some angle measure, which we'll call alpha, to another ray that would have an equation theta equals some angle measure, which we'll call beta. And our goal is to find a way to find the area of the region bounded by the graph of r equals f of theta from alpha to beta. So how are we going to make integrals do this for us? So let's think about what do integrals do? They add up infinitely many, infinitely small things. And what kind of things would that be in this system? Well, r always gives you the distance from the pole out to the graph that you're using. So it would give you as theta increases, you can see that the shapes that are created, if these were infinitely small, they would look like infinitely many, infinitely small sectors. So the area of the yellow shaded region here would be the integral from alpha to beta of just the area that we have here for the area of a sector. So it would be of 1/2 r squared. Now watch this. Instead of theta, if these are infinitely small, then this would be a very small change in your angle measure or a very small change in theta. And we have calculus notation for that. So instead of theta, you're going to see d theta. So the only difference between this and what we'll use most likely and what you'd see in a textbook is you would see that the area is the 1/2 would be factored out front, the integral from alpha to beta of r squared d theta. Now, a quick pause here. Some folks, when they see this, they really hate it that they've got r inside of a d theta integral, and that is very hateable. But please remember that r, right there, is something that we'll replace with an appropriate function of theta. So r is always defined as some function of theta, and we'll just be plugging that in. And this, my friends, is the area of a bounded region in the polar coordinate system. There we go. And that is the main idea behind part 1 of this lesson.